Hello, this lecture is on prototyping. Prototyping is the process of building a prototype. A prototype is an approximation of the product along one or more dimension of interest, reflecting at least one aspect of the product that is of interest to the PD team. There are four uses of prototypes in general. The first is for learning, which is answering questions about how the product works and is it good enough. An example of such a prototype is a proof of concept model. The second is for communication. We build the prototype so we can communicate to other people the product concept, to communicate it to customers, suppliers, or senior management. Many such prototypes exist: form, style models, 3D CAD models, look-alike models. The third is for integration, where we combine the subsystems into a single integrated prototype. Sometimes we test these subsystems independently, but they may not work together. Example of such prototypes are the alpha and beta prototypes. Finally, milestones. Prototypes are usually used in conjunction with project schedule and located at project milestones to verify the level of project completion, or can be used at gates in a stage gate project management system. Examples would include testable hardware. We can also view prototypes along two dimensions: scope and type. With scope, on the one hand, they can be focused or comprehensive. Focused prototypes implement one or few product attributes or features. Examples would be looks like and works like prototypes. Comprehensive prototypes, on the other hand, are generally an alpha or beta prototypes, and they are usually full scale and fully functional. Focused and comprehensive prototypes can be analytical or physical. Physical prototypes are tangible, and analytical prototypes are abstract, usually mathematical, like a simulation model or a system of equations to describe behavior. For example, in the Apple laptop example in the book, a focused physical prototype was built for the trackball support to learn about trackball feel. In contrast, a system of equations can be developed to model the behavior of the trackball support. Somewhere in between, which is less abstract and somehow more physical, is the use of simulation model for the trackball support. Finally, comprehensive models are usually physical. That's why you see this black area over here is the analytical comprehensive quadrant non-existent. These comprehensive prototypes are usually physical, as I said, and they are usually alpha or beta prototypes. Here is a summary of the comparison between focused and comprehensive prototypes. Focused prototypes implement one or few attributes of the product. They answer specific questions about a specific feature. Generally, several of them are required. On the other hand, comprehensive prototypes implement many or all the product features, and they offer opportunities for integrative testing, rigorous testing that involves all the functions and elements and the subsystems of the product, not a specific subsystem. And they're often usually used best at milestones for integration purposes. A summary for the comparison between physical and analytical prototypes. Physical prototypes are tangible approximation of the product, while analytical prototypes are mathematical in nature. Physical prototypes may exhibit unmodeled behavior because you cannot just model them. On the other hand, analytical prototypes can only exhibit behavior arising from explicitly modeled phenomena. Physical prototypes, some behavior may be an artifact of the approximation, while analytical prototypes, some behavior may be an artifact of the analytical method itself. Finally, Physical prototypes are often best for communication, to communicate the concept to either management or to your boss or to customers, while on the other hand, analytical prototypes are often allow more experimental freedom than physical models. More on comprehensive prototypes. Should we build them or not? Because they are generally expensive and sometimes we may not learn a lot from them. So this chart describes the cost on the x-axis in terms of time or money or both, and the risk on the y-axis, technical and market risk. In the first quadrant here, with the low cost and low risk, here there's no need for a comprehensive prototype, and if we do it for verification purposes only. For the book example, you usually see few chapters at a time. So limited prototypes and not comprehensive prototypes. Focus prototypes. Low cost but high risk. Here you build many prototypes. Serial and software are examples. When the cost and risk are both high, we build comprehensive prototypes, which you may actually sell, like the Boeing and the car example. Finally, when you have high cost but low risk, you may never build a prototype at all, like building construction or a bridge or an ocean liner like this. These things we have enough experience. No need to prototype. Traditionally, prototypes required special chops and skills and took long times to develop. They usually were developed using CNC machines and made of wood or foam, and making them required special skills. Now, there are numerous rapid prototyping technologies. Here are a few of them. And the list always is growing. 3D printing, SLS, selective laser sintering, LOM, laminated object manufacturing, and so on. All these rapid prototyping technologies have been enabled by 3D CAD models. You can actually have a physical prototype of any complex shape as long as you can capture it in a 3D CAD model. Usually we build parts and then we assemble them one by one. The key features of most rapid prototyping processes are first, these are additive processes, unlike machining, where it is a subtractive process where you take away material instead of depositing material. Here we start with nothing and we add materials progressively. These are usually built-in layers. Also, where the 3D CAD model is sliced into thin slices and material is built or printed or deposited accordingly, slice by slice. The most popular rapid prototyping method is stereolithography. It's also called sometimes 3D printing. It allows you to create solid 3D plastic objects from CAD drawing in a matter of hours. Virtual prototyping is assemblies of many 3D CAD models of subsystems and components which come together in a computer model and represents the full product. This is called a digital prototype or virtual prototype. From 3D CAD models, you can do lots of testing. Fit and assembly, manufacturability, form and style, kinematics, finite element analysis, crash testing, and many more. The advantage of these models is that they are much cheaper and faster to produce than physical prototypes and can provide lots of information. GM, for example, have used this technology to cut down on the time and cost of building physical prototypes. Building an automotive physical prototype usually takes around 4 to 6 months to build, to construct, with an average of around $500,000. Using virtual prototyping, an engineer could prepare a design model and simulate it in 2 to 3 days for about $2,000 instead of $500,000. A decade ago, General Motors built 80 physical prototypes at about $300,000 each to validate and test its designs for the cars. Today, GM builds about 20 prototypes only, and it does most of the other testing on computers. Boeing also developed its 777 airplane based on complete CAD models for everything, integrated CAD models for everything to the point where they could tell all their fit problems up front from the CAD model before building a single physical prototype. This is analytically, they will determine where everything goes together. BMW, you can actually do very complicated and sophisticated analysis that were just impossible to do on the computer, like crash testing, that is heavily used in the automotive industry. This is a virtual crash test where the computer simulates a crash test using finite element techniques. Recent advances in simulation software and computer speed make the virtual crash results very reliable and almost as good as the physical crash test. The advantage is that these physical crash tests are usually very expensive. A quarter to a half a million per vehicle. This is the cost of a crash test. These are prototypes, not production vehicles, so they are hard to make and they're expensive to make. Then you need to equip the car with sensors and crash dummies and then perform the test, which all add up to about $500,000 to test per car. So if we can eliminate this step or at least reduce the number of physical crash tests required with some virtual testing, we can save lots of money.